back to the final session this afternoon. Our first talk is Carlo Scandolo, who's going to tell us about operational axioms for diagonalizing states.
Good afternoon to everybody. It's a sheer pleasure for me to be here, and I'm very thankful to the organizer and the program and steering committee for organizing this conference and giving me the opportunity to give this talk. So here, as the title says, we are going to talk about how to define axioms that guarantee us that we can diagonalize states. So our idea is to include these axioms into a broader project as to the axiomatization of thermodynamics. And the reason to do that is because essentially thermodynamics is a theory which has application in a very broad spectrum of physical and not only physical theories in science, from biology to chemistry to physics. So one of the most intriguing and puzzling features of thermodynamics is definitely reversibility. And here we can see the example of the Maxwell's demon, which puzzled physicists for a long time and gave rise to a fruitful discussion between the role of thermodynamics and information theory. So we know that in classical physics there's a picture where everything is reversible because it's determined by the equation of motions. And then clearly one of the most coveted aspects of thermodynamics is just to find how to reconcile a description where we have irreversibility with a description where everything is reversible at some fundamental level. So in the classical cases, this is done by postulating a large number of particles and then treating the irreversibility in a statistical way. But now that also has some implication to the field of nanotechnology. So in this case, we have systems with a few number of particles and where quantum effects come up. So it's interesting to understand why we have this separation between reversibility and irreversibility and how to reconcile them. So since we have a strong relationship between information theory and thermodynamics, as pointed out by the famous Landauer's paradox principle, clearly we want to find the informational principle underlying the structure of thermodynamics, and to do that, one of the natural ways is to start thinking of informational axiom in GPTs, general probabilistic theories. So specifically, let me concentrate on the tool of majorization because I want also to link up to the interesting talk by Oscar. So here let me just remind the definition of majorization, and we know that this has featured as one of the most fundamental tools to understand thermodynamic transformation in the quantum domain. And the interesting thing is that majorization gives a preorder of quantum states based on their eigenvalues. So we want to explore these tools also to general probabilistic theories, and therefore we want to define the eigenvalues of states. So because also from majorization we have entropies as Schur concave function, which means function that preserve the ordering, actually the preordering given by majorization. So in this reference by Chirivella, Dariano, and Perinotti, there was a theorem proving that it's possible to define the eigenvalues of states, but they use the full axioms implying quantum mechanics. Here we only want to find the minimal set of axioms guaranteeing that, and hopefully this axiom needs to have also some thermodynamic significance. So I recommend you also to listen to the following talk, which will present a different approach to basically the same problem. So I will start presenting the framework and the axiom we are using to this axiomatization and find the diagonalization of states, and then I will briefly sketch how to diagonalize states if I have time. So we use a specific variant of GPTs which are known as operational probabilistic theory, which are slightly different from the GPTs Oscar presented in his tutorial. So we'll mainly follow the approach of the reference by Chirivella, Dariano, and Perinotti. According to this approach, we have circuits. So the focus here, instead of real numbers and real vector spaces, is on processes. Everything is thought to be a process. So here we have states like this, transformation represented as boxes, and effects. So the strong and rigorous foundation of this language is on strict symmetric monoidal categories, but I'm not going into that kind of details. So we can have two kinds of composition of transformation in sequence like that, or in parallel like this. And the interesting thing is that states and effects can be thought as particular kind of transformation where there's no input, like in states, so they are preparations, and there's no output, like in effects, that mean that destroy the system. So there's also a particular kind of transformation will play an important role in all this theory, which are called reversible transformation. And looking at this definition, this seems a very involved definition, but actually this means nothing that the fact that these transformations have an inverse in the sense of sequential composition, like as pointed out in these diagrams. So far I have only thought about the operational part of the theory. You may ask what the probabilistic part is. So now we come to that. So whenever we have a diagram without external lines, like this, we know that we can associate a probability with it. And clearly this gives rise to a notion of sum of transformation. In particular, we have that for states, we can associate a real values function with every state, which act on effects and gives the probability, the associated probability. This can be extended to more general transformations. Starting from this definition, we can define vector spaces, which are spanned by states and effects. And since everything is real, we have that these vector spaces are real. And then here I bridge the gap between the approach of this talk and the approach presented in Oscar's tutorial. So thanks to the notion of sum of transformation, we can define what a pure transformation is. And more generally, we can talk about coarse-graining, which is just the operation of joining together outcomes. So we say that a transformation is pure if the only way to write it as a sum of more elementary transformation is just to take these elementary transformation as proportional to the original transformation, where the coefficient is simply a probability distribution. That's the definition of purity. This is a general notion which makes sense also in general probabilistic theories. Now we start with our axioms. So the first one is called purity preservation and appeared for the first time in this paper. This axiom says that whenever we compose pure transformation, either in sequence or in parallel, we get another pure transformation. Specifically, we have that the product of two pure states is pure. So why we are going to assume this axiom? So if this axiom didn't hold, then we would have some kind of very weird behavior about how information is lost. Here I call it some kind of non-local loss of information. Let me explain it better. So consider this two transformation, let's call it A, and here B. And we are supposing that both of them are pure, which means that they carry maximal information. They also preserve maximal information when they occur. So this is pure, and this is also pure. So if the composition weren't pure, this would mean that there would be some kind of leak of information here, which is not localized either in A or in B, but just on the fact that we are just composing and putting together two transformations. This seems some kind of unreasonable behavior, so we are going to assume that axiom. Also thinking of a theory as an algorithm to make some prediction about physical transformation, about physical processes. So whenever we are provided with maximum information, it's rather natural that also the outcome of that algorithm will also present maximal information. And then we are moving to the following axiom, which is causality. So here we started from purity preservation because purity preservation doesn't need causality. So causality is defined according to the two papers as, roughly speaking, that the fact that the outcome probabilities of present experiments are not affected by future measurements. So besides being a rather natural requirement for physical theory, this has also some thermodynamic significance. And this is done and seen through the following property. Through the fact that causality is completely equivalent to the fact that for every system there exists only one deterministic effect, which is called TR8 in analogy with the trace in quantum mechanics. And why is this important? Because through this deterministic effect we can define the marginal of states, which means that whenever we have a bipartite state we can always discard a system and to deal with another one. And clearly this is very important in thermodynamics because thermodynamic procedure involve restricting to subsystems and also enlarging to the system to deal with isolated systems. So in this way, causality seems a natural way and a natural requirement to do thermodynamics because we have a canonical way to restrict ourselves to subsystems. So I talked about enlarging the system. Now we present the postulate or the axiom, as we might prefer to call it, that ensures that we can do that. And this is called purification. So purification appeared for the first time in these two papers by Chiribella, Adriano, and Perinotti about the derivation of quantum mechanics from information theoretic principles. So this axiom is made of two parts. The first one is that every state rho can be purified, which means that every state rho arises as a marginal of some pure state. And the second part is that whenever we have two pure states giving rise to the same marginal, they must differ only by a reversible transformation on the purifying system, which means that if we think of A as the system and B as the environment, so whenever we have the same situation, the same dynamics on the system, and we purify, basically the situation, the complete picture is blocked. I mean, the only possible difference is some kind of transformation on the environment and involving only the environment. And the important thing is that this transformation is reversible. So this is nothing but the purification theorem of quantum mechanics, which is here turned into an axiom. So why are we going to assume that axiom, which might sound strange to some of us? So this means that whenever we have partial information, means a generic mixed state, we can always go to a picture where everything is pure, and not only pure but also reversible, as it's being proven. So this means that this is a good starting point to achieve some kind of reconciliation between the pure picture and the mixed and partial information picture, which is common and widely present in thermodynamics. So another interesting point is that all dilation and extension theorems can be reconstructed from this purification principle. So meaning that every non-reversible dynamics can always be interpreted as some kind of reversible dynamics occurring in a larger system, and after that we trace out, we get rid of some of the system involved, specifically the environment. So this means that we are formally entitled to enlarge a system to have an isolated system, whereas in classical thermodynamics this procedure is only heuristic. There's nothing from a rigorous point of view that ensures that we can enlarge a system. But in quantum mechanics, where purification holds, and also in theories where purification holds, we can do that. We are sure that we are officially entitled to enlarge a system to have an isolated system. Therefore, we argue that purification is a good starting point for a theory of thermodynamics, whichever it is. So the last axiom we are going to assume to achieve diagonalization is pure sharpness, which states that for every system there exists at least one pure effect that occurs with unit probability on some state. So we can think of this effect as testing some kind of elementary property of the system, because because the effect is pure, so it can't be further decomposed into a sum of other effects. And this ensures that every system possesses at least one elementary property, and this can be interesting from a logical point of view. Now, combining the pure sharpness with purification, we get some interesting consequences. The first one is we have a complete duality between pure states and pure effect. So for every pure state alpha, there exists a unique pure effect alpha dagger, such that this pure effect yields 1 on that state, and vice versa. So for every pure effect, there exists a unique pure state where, when they are composed together, they yield probability 1. The second interesting point is that this axiom doesn't assume the fact that the states are perfectly, there are perfectly distinguishable states, but here we can prove it as a consequence of pure sharpness plus purification. So there are some perfectly distinguishable pure states, and these are the basis of the procedure to diagonalize states. Indeed, we define a diagonalization of a state as a decomposition of that state in terms of perfectly distinguishable pure states. And we call the coefficient of such a decomposition as the eigenvalues of the diagonalization. So in order to achieve that, let me briefly introduce some notation. So for every state we define a P star, which is the maximum probability with which a pure state arises in a convex decomposition of the state we are interested in, which is rho, so that we can see that. So clearly there's a pure state associated with that kind of P star, and if we take the effect alpha dagger associated with that pure state, which gives P star, so we know that this effect applied to rho gives exactly P star, and as a consequence, if we apply this effect to sigma, we get that this effect to sigma yields 0, and this also yields 0 for all the pure states contained in sigma. And this is the starting point for our algorithm to diagonalize states. So when we have a state rho, the first step is to determine P star, and we call here Q1 and the associated state alpha, such that we can write this. And then everything is very simple, because we just repeat the same procedure for the state sigma 1. And so on. Here we find the maximum probability Q2 and the associated pure state alpha 2, and then the state sigma 2, and then we iterate the procedure. In the end, so we get the decomposition of rho in terms of pure states, where the coefficients are defined as follows, as one can easily check from this algorithm. That the important part is the following, that so the effect associated with the state I yields 0 on all the states with index greater than I. Let me explain briefly why. So suppose we are considering alpha 1. So alpha 1 dagger, according to the previous slides, yields 0 on all the pure states contained in sigma 1. And the pure states contained in sigma 1, according to this procedure, are nothing but alpha 2, alpha 3, alpha 4, and so on. And again, so we can do the same for alpha 2. So we can take the effect alpha 2 dagger, and this yields 0 on all the pure states contained in sigma 2. And in this way, we just have again this property, and because all the states contained in sigma 2 are nothing but sigma, alpha 3, alpha 4, and so on. So these are just technical details, and if anybody is interested, I'm very happy to talk about it perhaps during the question time. Let me just skip to the conclusions. So with purity preservation, causality, purification, pure sharpness, we manage to diagonalize states, because we can prove that the definition we give of actually the property we just exposed about the pure states, such that the pure effect associated with alpha I yields 0 on all the other alpha j with j greater than I, implies that these states are perfectly distinguishable from each other. And this is not clear at this point from this procedure, but we have still working on in this paper. Just some kind of forthcoming paper where we just prove that actually the diagonalization defined this way has the property that all the eigenvalues of a given state don't depend on the procedure on which we diagonalize. So all the diagonalization of given states have the same eigenvalues. Therefore, we have the eigenvalue of states, then we can define spectral majorization, and therefore sure concave function like entropies. And this was initially done in my master thesis. And finally, we want also to connect this work with a previous work about LOCC transformation in general probabilistic theories and resource theory of purity. And if we add this axiom that reversible transformation act transitively on maximal sets of perfectly distinguishable pure states, we have a full equivalence between the notion of majorization introduced in this paper as a consequence of the diagonalization procedure and the ordering of states given by random reversible transformation in this resource theory of purity we have defined. And here, that's all. I would like to thank you for the attention, and I'm going to give you some references.
Excuse me. We have some time for questions. Any questions? Dan?
Yeah.
Do you have an algorithm for calculating P star?
No, unfortunately not.
Okay.
So we just define it, and so we don't know how complicated it is to calculate actually P star. We just assume that we can calculate it. Yes?
Yeah, so I was wondering, the axioms you use in your derivation, how many more axioms do you need to add to those to get back to full quantum theory?
Yeah, so this is an interesting and important question actually. So these are not the full axioms implying quantum theory, because there are other two axioms necessary to retrieve quantum theory. Actually, here we are assuming also a slightly weaker axiom than the one originally presented in this paper, which is about the information derivation of quantum theory, because pure sharpness is here, replaces the distinguishability axiom, which was originally presented in this paper. And the other two axioms missing are the so-called perfect compressibility, the fact that whenever we have a larger system, we can, it's best understood in the case of quantum theory. So if we have, for example, in dimension 10, but we have only a density matrices with rank 2, we can always compress the Hilbert space to deal with the Hilbert space with dimension 2, because the other degrees of freedom are not involved. This is basically the content of ideal compression. And the other important thing is local tomography. So here we're not assuming that. So for example, in this treatment, real quantum mechanics is included. Okay.
I would like to know how you to explain us more how you make the equivalence between your definition of causality and the existence of this transformation, the trace.
Well, because clearly, well, this is perhaps you can discuss it a little bit later. But just if you want to know the mathematical definition of causality, it's simply the fact that whenever we have a different preparation of the states, right, this way. Suppose we have rho 1, rho I, sorry, and then we take two observation tests, which are simply collection of effects. So Ej, here we have also Ck. So the causality condition is nothing but the fact that when we sum over J, some kind of no signaling from the future, sum over J of Ej applied to rho I is simply equal to the sum over K Ck rho I. And this can be easily linked to the existence of deterministic effect. Because when we sum over all the possible effects, here we get a deterministic effect because there's no ambiguity on the outcome. That can be found with certainty. But we can also talk about it later. Yes.
So, I was wondering how much you need the one part of the purification axiom, so the part that there always exists a purification, because I think that you could have a theory of quantum theory in one part of the universe. It's like you might not be able to find all purifications here, but I should still be able to do resource theories in some
Oh yes,
clearly. So I should still be able to do this to find some kind of marginalization, diagonalization. So how much is this?
Well, clearly, in classical probability theory, we have majorization, and clearly classical probability theory doesn't satisfy purification. Clearly, so these axioms are not necessary; are just sufficient to imply majorization and the existence of the eigenvalue. Here, actually, we want. Our main aim is just to find the axiom leading to some kind of reasonable theory of thermodynamics. And here, besides of the results I get from purification, I'm also willing to assume it from its, let's say, conceptual relevance about the fact that we can always extend systems to deal with isolated systems. This is essentially one of the compelling reasons to assume that axiom, besides of the results one gets.
But you need to derive your diagonalization process. You need the axiom.
Yeah, in this way, yes, clearly. We need it. Well, otherwise I wouldn't have presented it.
Okay, we should move on, so let's thank